Let's measure Hubble's constant H subscript 0 using Python. Two ways to do this are using the supernova data and the cosmic microwave background data. Let's use the supernova data. It's a text file separated by spaces. So let's download the text file and separate the lines by spaces, skipping the first line. We take two columns and set those to the z and mu properties. So z and mu are redshift and distance modulus, and plotted it looks like this. The code for this video is in a notebook that's linked to in the description, and you can get everything you need there. How do we use this to measure Hubble's constant? Let's look at some example data and say that y equals ax, and we're trying to find the best fit for a. So let's pick a value for a. For each data point, we subtract the actual y from ax, and then square that difference, and then add them up all together. We can do this for a variety of a values. What we're doing is we're looking for the smallest sum. That's the best fit, and that's the one we'll use. For the supernova data, instead of x we have z redshift, and instead of y we have mu distance modulus, but the steps are really the same. We're just looking for the lowest sum, and that's our measurement. This code looks at every supernova and calculates a mu and compares that to the mu in the data. The difference is then squared and then added to a total. To calculate mu, we'll use Cosmolopi's distance modulus function. This calculates the SSE for each value of H subscript 0 between 65 and 75 and reports the lowest value, which is 73.2 kilometers per second per megaparsec. So we just measured Hubble's constant. It's 73.2. All the values tested are shown here. And this is for the standard model of cosmology using specific parameters, 70% dark energy exactly. We're not using error bars or uncertainties. We could, it's just one more step. But the uncertainty in the data says do not fit cosmological parameters with these uncertainties. So I didn't. So we measured 73.2, but the cosmic microwave background data says 67.4. This is known as the Hubble tension, and this is the standard model of cosmology, lambda CDM. In episode 8, I introduced the time-dilated past hypothesis, which is an alternative model of cosmology. To calculate mu in that, we use this distance function. So we changed the calculate mu code to this. Rerunning the calculations with this new code gives us an output of 70.4. So Hubble's constant is now 70.4 kilometers per second per megaparsec. Here's the alternative model compared to the standard model. And you see that the standard model has a lower dip, so it is a better fit. So what do you think? Did you learn something? Have any questions? Have an idea for the next video? Leave a comment, subscribe. Thanks so much for watching.